And then we'll go back to you. And then. Perfect. And then, yeah, I think whenever you are ready, you're good to go.
Good. Welcome, everybody, for our, I don't know what number we're up to, 6 things. So
We're up there.
somewhere there. So I'd like to introduce our speaker today, Sean Young, who is a doctor in the, or is assistant professor in the Department of Geology or Geological Science at UF here, specializing in hydrogeology. His research investigates the coupled dynamics of groundwater flow, solute transport, geochemical reactions, and microbial activity to reveal how these interactions shape ecosystems, influence environmental quality, and affect water resources. And being a surface water guy, I can imagine your world is much more difficult to interact with than mine. Because we're up here and then you're looking at what's underfoot. So either way, it's all yours. Thank you.
Welcome introduction. Hello, everyone. Thank you for coming. It is a pleasure. My research area is hydrogeology. That is the branch of geology studying the movement and distribution of groundwater and how it drives the fate and transport of solutes dissolved in it. And studying groundwater flow and the solute transport typically indicates answering to these questions. So first, where the groundwater and solute like contaminants are coming from, and where they are going, and how long does it take, and how they will change by decaying or reactions, geochemical reactions. Answering to these questions are quite challenging, mainly because the subsurface geological systems are controlled by multi-scale structural complexity. So if you consider this catchment scale of subsurface groundwater system and zoom in further, then you will identify this pretty network scale system where the flow and transport is heavily controlled by the interconnectivity between the rock fractures, which are the main pathway for groundwater flow and solute transport. So if we zoom in further, then you will identify this small single fracture scale system where the flow and transport processes are controlled by the fracture surface roughness. And if there is mass exchange between the rock matrix and the fractures, then the flow and transport processes become more complex. And throughout these different scales, there is very critical phenomenon widely observed across scales, that is anomalous transport, often known as non-Fichtean transport. So anomalous transport is the counter concept to Fichtean transport. So Fichtean transport is the process that can be fully characterized by these well-known governing equations, including Fick's law and the advection dispersion equation. And in Fichtean transport system, the solute spreading in groundwater system can be modeled by this nice Gaussian type distribution. And if we measure the concentration of the solutes at the outlet of the system, then its evolution, we often call it as a breakthrough curve, shows this bell-shaped curve. In contrary, in anomalous transport system, which is, although the name is anomalous, but that is norm in subsurface systems, and the solute spreading cannot be described anymore with this nice Gaussian type of curve. And if we analyze the breakthrough curve, it has two critical differences compared to the Fichtean transport. First, it is showing very enhanced early arrival of the solutes, and at the same time, we observe this late time tailing behavior, often in power load shape. And if we are looking at the anomalous transport system, then it has a lot of implications in environmental aspects. For example, the lifetime tailing would mean that the contaminants would be undergoing the extremely long retention in the system that can cause a lot of environmental concerns. And this anomalous transport behavior is widely and ubiquitously observed in different hydrogeologic systems, including hyperic zones and the stream channels and even karst aquifers. And my previous study was to investigate the source or the mechanism of anomalous transport at different scales of fractured rock aquifers. And I will first start with scale study. And the first site is located within the campus of University of Minnesota, where I completed my postdoc training. And the Mississippi River flows right through the university campus, and the first site is located on the west bank of the river. And at the time, my office was here at home, the Earth Science Department at the university, and it is just 15 minutes away by walk, so I could enjoy the fieldwork. But not only the proximity to my office, there are many great pictures of this site for investigating the anomalous transport mechanisms. First of all, there is a cliff area facing the river, and from the cliff we could access these outcrop images from which we can trace the fractures. And there is very important geologic feature, hydrogeologic feature, that is this bilateral parting, which is highly conductive. So most of flow and transport processes occur through this highly conductive bedding plane. And there is an underground space excavated for parking lot space. And if you get into the parking lot and look up the ceiling, then you can assess this the bottom outcrop of the limestone layer of the site. So from these outcrop images, we could extract the information about the fracture orientation, length distribution, and density. And if we look at the cross section of the site, the limestone aquifer is underlain by impermeable shear layer, and this is the excavated empty space where we could assess the outcrop in the ceiling. And the limestone layer is underlying the top soil layer, and it is almost throughout the first site, the limestone aquifer is almost mostly fully saturated. And this site is heavily contaminated by petroleum products. And due to the high conductivity through this bedding plane, most of the contaminated water moves through this bedding plane. So to handle that contaminated water, the university installed horizontal well there so that they can collect most of the contaminated water through the bedding plane. And due to the operation of the horizontal well, the first site shows a very strong hydraulic gradient and strong groundwater flow. And to characterize the anomalous transport behavior in this site, we conducted eye tracing experiment. So there is a monitoring well 100 meter away from the horizontal well, and we injected fluorescent dye and sampled the water from the horizontal well and estimated the concentration of the water samples we collected. And this is the breakthrough curve that we analyzed, and again we observed very strong lifetime tailing behavior. And our question was like, what is the mechanism or source of this strong lifetime tailing, this anomalous transport behavior? To investigate that, we generated a numerical model where from the outcrop images, we extracted all the information about the fracture networks, and based on that, we create this discrete fracture network and coupled it with rock metrics to consider the interaction between rock metrics and the fractures. And from the flow and transport simulations, we investigated sensitivity of different parameters, and we identified two major parameters. One is rock matrix permeability. So in these two simulation cases, the difference is only the rock matrix permeability. By increasing the rock matrix permeability, we could enhance the lifetime tailings. Here, the black line is the simulation results, and the blue line is the observed the breakthrough curve data. So this results means that the active mass exchange between the highly permeable the bedding plane and the low permeable rock matrix can delay the transit of the solutes so that we can observe this lifetime tailing behavior. Another parameter is pressure density. Here, pressure density is defined as the level, the number of fractures. So low pressure density means less number of fractures within the system, and the high pressure density means a large number of fractures within the system. And by lowering down the pressure density, we almost capture the lifetime tailing behavior. And can you guess why lowering down the pressure density can kind of capture this lifetime tailing behavior? So this is the last time step snapshot of the flow and transport simulation. And as you see here, this right panel is when we have low pressure density, and this is when we have high pressure density, as you can recognize easily from the image. And when the low pressure density is the condition that we are looking at, we have many not well connected dead-end zones where the solutes are trapped. So those trapping effects can delay the solute transport processes, causing the lifetime tailing. So please remember this result, because this will be repeated in another scale system study. So to wrap up this scale study, we found that the flux exchange between rock matrix and fractures for the bedding plane can cause the lifetime tailing. And we also confirmed the dead-end fracture effects on delaying the transport processes, inducing the normal transport behavior. So next part is the fracture network scale study. So if you Google the word fractured rock, then these are the images popped up. And as you can see from the images, the complexity of the fracture network is quite uncertain, and it is widely spread. And so it is quite challenging to identify which structural factor is causing the anomalous transport behavior. So our approach is to utilize machine learning model. And machine learning model is a black box model connecting the input and output data. And once we could train the machine learning model, then we can ask which is the most important input parameter here. So our idea is that if we can extract the structural features from the fracture networks as input data and provide the resulting slope of the breakthrough curve for each fracture network as output data, and by providing those input and output pair data to the machine learning model, here random quest, then we can, by training the model and asking the model to identify which structural property is the most important one, we can identify the cause or source of the anomalous transport in fracture network scale system. So for this, we generated a large number of fracture networks, changing different parameters like fracture networks, fracture density, fracture orientation parameter distribution, and fracture length distributions. And for all realizations of the fracture networks, we using graph theory, we extracted structural features. And I will not go in detail about each structural features we extracted, but let me just cover the percentage of dead-end fractures. So any fracture network can be converted into a graph network. Here, each node in the graph correspond to each fracture in the fracture network, and the links between the nodes are indicating the connectivity in between fractures. And here we also can identify the inlet and outlet points of the fracture network. And from this graph representation, we can identify the main pathway connecting the inlet and outlet nodes. And those nodes or those fractures do not participating in that main pathway are defined as dead-end fractures. And we estimate, so using this graph representation, we could estimate for each realization fracture network, the percentage of dead-end fractures. And so we estimated, we extracted the structural features as input data. And for all realizations, we run flow and transport simulations, and we estimated the breakthrough curve and estimate the tail slope. So now we have the input and output data to be used for training the black box model. And this is the result that the random forest model provided in terms of which input parameter is the most important in determining the latent hailing behavior. And the random forest identified the dead-end fractures percentage as the most important feature in determining the tail behavior of the breakthrough curve. So to deepen our understanding about this result, we compared the dead-end fracture area and the tail slope across different fracture density, and we see some correlation between dead-end fractures and tail slope. And this means that, and this can be related to our first part results, where we see this enhanced tail slope when we have low fracture density. But in this research, we found that not only the minimum, not only decreasing, but there is some optimum level of fracture density that induces the biggest dead-end fracture area, and thereby inducing the most significant tailing behavior. So yeah, these are the two main findings of this study. Now, so let's move on to the smallest scale, that is single fracture scale system. So most of the existing studies about flow and transport processes in fractured rock systems adopt very strong simplifications and assumptions. First, they usually assume flat fracture surface, and even the flow structure is simplified by this plug flow that is, but these assumptions are valid when the flow velocity is quite low, like laminar flow. But in fracture flow, due to its high conductivity, we often observe very strong flow velocity, even turbulent flow. So this is the borehole video captured by Minnesota Geological Survey. And as you can see, there is a horizontal fracture cutting through this borehole, and the groundwater is actually indeed gushing out, indicating very fast velocity of the groundwater flow through the fractures. And to investigate the effects of the fast flow velocity and the pressure lockings, we did some experiment using microfluidic systems. And for those of you here, I brought the microfluidic chip that I used to create this video. Please pass around this chip and you will see how small the system is. So we changed the flow velocity. So here the flow velocity can be represented by Reynolds number. And even with the rock fractures, when the flow velocity is quite low, we have nice flow path line that is parallel to each other. But when we increase the Reynolds number, we observe the formation of these recirculating flows that is due to the inertial effects. And So we also did some computational modeling. So by changing the roughness and we could capture this recirculating flow effects. And due to that recirculating flow, so the solid particles are easily trapped in that recirculation zone, and that causes the delay in the transit of the solid particles. And when you look at the breakthrough curves, we see the enhanced canning behavior in rough conditions. And that is mainly coming from the trapping effects of the solid particles in the recirculation zone. So from this small scale study, we found that the pressure wall openings will cause recirculating flow in high velocity condition. And those recirculation zones can trap the solid particles, thereby inducing anomalous transport behavior. So far I have demonstrated how the hydrogeology study, like studying flow and transport, can be multi-scale science. But the hydrogeology is also a multi-physics science. For example, due to the fluid and the rock mineral interaction, the rock minerals can be dissolved into the fluid phase. So such a rock dissolution process can deform the pore space within the fractures, impacting the flow and transport processes. And if the fractured rock system is under confining stress, then the pore space also will be deformed, and that deformation is known to cause very strong anomalous transport behavior. Even the formation of biofilm within the fracture space can cause different flow and transport behaviors. And as an example of my ongoing research in this multi-physics approach, I will show a collaborative work that I collaborate with Dr. Chang Wong here. And this is my group's approach regarding hydrogeologic systems. So we always try to consider the effects of structural complexity and the groundwater flow mechanism, like fluid mechanics and solute transport, geochemical reaction, and microbial processes. And this will be a good example adopting that integrated approach. So this work is about nitrogen cycling in karst aquifers. And the nitrate contamination is a major environmental concern worldwide, even including in Florida. And unfortunately, so nature has a built-in mechanism to mitigate that problem, that is microbial denitrification. And microbial denitrification is a series of redox reactions in which the nitrate is sequentially reduced to nitrite, and then to nitrous oxide, and ultimately to nitrogen gas. And each step of this denitrification process is catalyzed by specific enzymes produced by denitrifying microbes. And the DNA genes encoding these enzymes have been well characterized, as indicated by the blue letters here. And for this denitrification process to be completed up to the nitrogen gas, this system should be in anaerobic condition. In other words, oxygen depleted condition. And that condition can be typically satisfied for deep subsurface groundwater systems due to the isolation from the atmosphere, and the active microbial respiration process can easily consume the residual oxygen within that deep subsurface region. The karst aquifers can be different. So karst aquifers are characterized by the carbonate rock dissolution features like sinkholes and conduits. And these dissolution features can be rapid pathways for oxygen-rich surface water, easily reach and mix with the oxygen-depleted groundwater. And such intrusion of oxygen into this oxygen-depleted system can inhibit this denitrification processes. And that inhibition can cause, for example, the accumulation of intermediate nitrogen species. And in particular, we are interested in the nitrous oxide, which is a very powerful, potent greenhouse gas, almost 300 times stronger than CO2 in terms of warming potential, and it is also a ozone depleting substance. Sorry. So to investigate the effects of surface water and groundwater mixing on this N2O dynamics, we conducted a field scale study. The field site is the Santa Fe River synchronized system in Orlando State Park. And it is 40 minutes away by driving from UF campus. And thanks to the USGS gauging stations installed at the sink and rise, we can track in real time the discharge into at the sink and rise. So here the river. So let me share the interesting picture of this field site. So the Santa Fe River enters into the ground at this sink, the large sink, and it travels through the conduits, underground conduits for over 7 kilometers, and it re-emerges at this first magnitude spring known as the river rise. And we, as I said, we have the discharge real-time discharge data at those 2 locations. And if the input, the discharge at the sink is larger than the output, the discharge at the rise, then we can say that the surface water, the oxygen-rich surface water, is recharging the surrounding the groundwater system. And that can be identified by this gray area. So for this mixing event occurred in January this year, we went out to the field and sampled the water from 3 locations. These 2 monitoring wells, well 3 and 4, and this river rise. And the river rise is just river water, so it is representing the surface water end member. And here the 2 monitoring wells are screened at the depth of conduits, but the well 3 is 30 meter and well 4 is 120 meter away from the conduits. So different distance to the conduits will have different mixing significance or level. So this is the isotope data from those 3 locations. So as I mentioned, the river water have clusters in this area, the heavy water region, and the groundwater, which is the well 4 waters, are located here. And the well 3 water samples are located plot intermediate values between these 2. So this data demonstrates the active surface water and mixing, surface water and groundwater mixing at well 3. So we estimated the dissolved N2O level from those samples from the monitoring wells, and we see very dynamic changes in N2O level at well 3, whereas well 4 shows unresponsive behavior. So this means that the active surface water and groundwater mixing causes the elevated N2O at well 3. And what is the mechanism of that would be microbial processes. And to investigate that, we estimated the DNA genes from well 3 samples, and we targeted these 2 genes, NOS and NIR. Here, NIR is for producing N2O, and NOS is to reducing the N2O. And as you see here, the NIR to NOS ratio rose and fall in parallel with the N2 level. But there is some lag time. So that means that the denitrifying bacteria that can conduct this N2 production will maintain its abundance compared to the denitrifying bacteria that can do this N2 reduction, so that it can cause this prolonged N2O level. But this DNA data does not explain fully the early elevation of N2O. And to interpret this data, we have to consider the central dogma in microbiology. So I learned this from Dr. O. And so the denaturifying bacteria carrying this DNA gene transcribe and translate to produce the enzymes. And these enzymes are immediately responsive to the oxygen intrusion. So once the oxygen comes in, then these enzymes will be immediately inhibited. That's why we see this early elevation of N2O. But later, due to the lack of respiration pathway due to the oxygen intrusion, the denaturifying bacteria will change its abundance that we observed by these ratio changes. And that ratio changes were the different the evolved the composition of denaturifying bacteria will prolong this elevated N2O. So to confirm this field scale hypothesis, we again conducted this micro scale experiment. So this is the microfluidic chip that I used for this experiment. Please pass around. So the microfluidic chip has 3 injection ports. So here, these side ports are for injecting oxygen depleted groundwater, and this left port is injecting oxygen rich surface water. And here the channel is representing the conduits, and the surrounding area is full of these small pillars, and they are representing the rod aquifer, the porous medium. And by changing the surface water injection rate, we induced different level of surface water and groundwater mixing. And as we increase the mixing level, we could observe we collected effluents from this port and analyzed the N2 level, and we see the increase of N2 level as we induce more surface water and groundwater mixing. But at the same time, we also analyzed the DNA levels from these fluid chips, and these N2 elevations were observed in early time regime within 80 minutes somehow or so. But during that time window, we did not observe any changes in DNA. So this result confirms that the early N2 production is controlled by the enzyme inhibition, and then the later DNA abundance change or composition change will prolong that elevated N2 level at the field site. So in this seminar, I demonstrate that the hydrogeology is a multi-scale and multi-physics science, and this is our main research direction to consider different physics and processes. Thank you for listening, and I would be happy to answer any questions.
Questions in the room?
Question.
Yeah.
Thanks for the night talk. I have a question about the anomalous transport phenomena. So you mentioned high permeability, low fracture density can enhance the late time tailing effects. But I guess the low fracture density is the reason why we have that cognitive effect with the low fracture density is because of the dead end. What if we have low fracture density, but those fractures are interconnected? And are we gonna see still those effects, or?
Yeah, so for example, you can think of horizontal and parallel fractures. connected to each other tip to tip,
Yeah,
then ultimately it will be just single fractures.
right,
But
yeah,
in such extreme case, then even with low fracture density, the dead end effect will disappear. But that is not kind of natural condition in
so I
nature.
guess the basic assumption or fundamental assumption in this geology is you have this bedding plane. And fracture is basically perpendicular to that bedding plane direction.
So
That-
that is, so yeah, that is very good question. So the condition that you just described is specific to the field site that I studied. For the fracture network scale system study, we assumed a random orientation and the length of the fractures. And that is more natural conditions in nature. And in that system, I demonstrate that the dead end fractures are the main the source of anomalous transport. But back to your initial comment, even in that system, if those fractures are aligned well in terms of orientation and the connecting points are kind of tip to tip, then even in that case, in such case, the dead end effects will disappear and we will not observe the anomalous transport.
I see. Can I ask one more? As far as the, what was that, the Reynolds number case,
Mhm.
you said there's a eddy currents that
Mhm.
trap salts there.
Mhm.
Can you scale the roughness feature size as with the Reynolds number somehow? Because we can scale the eddy current size with the Reynolds number.
So here, the system are not turbulent, it is still laminar, but here the eddy is the small scale eddies like in turbulent flow. It is still laminar flow, but due to the roughness, so the Reynolds number here is just 100, not over 1,000 or.
Yeah, so I
10,000.
mean, for the same roughness feature size, or low Reynolds number, we didn't see that eddy current.
Right.
And for Reynolds number above certain point, we see that eddy current, right?
Yes.
Can you find like that critical Reynolds number for given roughness feature size?
Oh, the
So
critical,
what's meaning about the scaling between those two?
so. First, let me clarify your question. So are you asking about, like, is there any threshold of Reynolds number determining the formation of eddies? Yes, there are, and but that threshold level of Reynolds number determining the formation of recirculation flow will be also depending on the level of roughness.
Sure.
Right. So I don't anticipate to find a universal criteria that can be applied to any.
But we can get that correlation, right, between the threshold Reynolds number as a function of roughness feature size. That
So here, regarding the generation of rock surfaces, I use a self-affine self-affinity. So self-affinity here is like if you zoom in surface, that kind of roughness will be maintained. So, and that roughness level is controlled by the parameter known as Hertz exponent. And I just changed the Hertz exponent to change the level of roughness. And so let me explain maybe once. Yeah. So I want to show the video. Yeah, here. So in terms of the trend, these three rock fractures are the same, but by changing the Hertz exponent, we see the different curvatures, and that is the main source of the roughness of the fracture surfaces. And even with this intermediate rough condition, by increasing the Reynolds number further, we can enlarge the recirculation zone. So it is kind of compound control on the recirculation zone formation, like the Reynolds number and the Lockins level. So I don't fully capture your question, but we can talk later.
Sure.
Rob?
So it looks like so if you simulate like those breakthrough curves with those different configuration, you mainly use like particle tracking.
Yes.
Right?
So for this small scale system, we utilize particle tracking algorithm. But for the pre-scale study, we used continuum scale transform model.
Okay. But then, for example, like you also have like a picture like this for the discrete fracture network. I also saw like this front, if it goes kind of like through those fractures, it looks like particles, right?
Right. So I use the continuum scale advection dispersion equation only for the field study. And for this intermediate fracture network and this single factor scale, I simulate the solid transfer by the particle tracking algorithms.
And is that the particle tracking with like a random ball?
So two steps. So advection and dispersion. So in this small scale advection diffusion. So the advection is simulated by letting the particles follow the flow path. And every advection step, the particles undergo the random diffusion, that is diffusion process.
Okay. No, I'm just asking this question because like it's interesting part, like you would, like if you would only do the advection part, then still you would get like they typically because like they follow like different paths, so you get you say that.
So I don't know.
Like this tailing effect, like if you just do this like affecting particles, right? And you get this tailing effect that is basically just reflecting that they follow the different flow paths. Like some particles will find the fastest way, and some particles they kind of they go through multiple fractures or they get stuck in this kind of stagnant zones here. So they just simply they arrive later.
Yeah, so let me clarify. I think I understand your question. So if you look at the breakthrough curves, there are two time regimes, late time regimes and early time regimes. And the early time regimes are controlled by merely advection. So the particles moving through the path, flow path lines are corresponding to this behavior, the early time arrival. But the late time arrival behavior, of course, determined by low velocity path lines. But if we don't have diffusion effects, then we would not see this late time tailing behavior. Because if we don't have diffusion, molecular diffusion, then this boundary between the main pathway and the stagnation zone is divided, and this acts as a slip boundary. So the particles moving through the boundary here can be trapped into the recirculation zone whenever they go through the diffusion. So diffusion is quite important. Diffusion or dispersion is quite important phenomenon to induce the anomalous transport.
I've just always been kind of like surprised a little bit. Like if you do those two different ones, let's say like particle tracking and advection dispersion thing, that the dispersion that you put in this advection dispersion equation, like that one, the dispersion is then like you, that depends on the concentration gradient. You see, like every second order DC.
Yeah. So advection dispersion equation is
which is funny because like it always struck me a little bit like there's no reason if you look at a thing like an aquifer that this dispersion like this like they call it like a mechanical dispersion. I think that they look it basically means like they always show like they follow different paths because they show it maybe like it's porous kind of like things or there's like different flow paths. But then actually in the advection dispersion equation you nicely make it a function of like some concentration gradient. This makes you see it's more for gas or something, but not for.
But theoretically, advection dispersion equation can be converted into particle tracking equation, the Langevin equation. When we have but we need the limiting condition like the large number of particles. So theoretically, they are the identical. And advanced dispersion equation, but the main description is based on the concentration gradient. And that concept is still valid in this particle tracking algorithm. The concentration is the density of the particles at certain unit region. They are interchangeable.
Questions at all?
No questions online.
I have one question. You mentioned about biofilms and growth and how that could influence this, and kind of using this as an example, I'm curious, any speculation on would the biofilm kind of fill in and reduce the volume of that recirculation trap? Or would it almost accentuate because it's gonna grow faster, perhaps where there's a higher nutrient availability or something like that?
That's a great question. And actually, we are going to investigate the effects again in this small scale approach. So here we didn't, so in this study, we wanted to avoid that clogging effects by the formation of biofilm because we have to induce this nice surface water and groundwater mixing behavior. But to induce such a nice flow phenomenon, even with the formation of biofilm, the channel height, so into this spring wide, is on 200 micrometer. So micrometer sounds very small, but in terms of view of micro, that is huge space. So they never clog the space, pore space. But in natural porous media systems, the biofilms are very well known to clog the pore space. And that clogging effect can cause a very different flow behavior, like preferential flow. And the formation of preferential flow means that very fast direction of the solutes through the preferential flow. But due to the mass exchange between the preferential flow and the surrounding slow velocity region, can delay still the anomalous transport behavior. And that is kind of our future direction in this approach.
Any other questions? Well, thank you very much.
Thank you.
Yeah.